Welcome back to Bio 6612. For this week and the next couple weeks, we're going to talk about longitudinal data analysis. And this lecture will serve as an introduction to longitudinal data, and I'll also mention some other models that we're going to consider later in this course. So there's cross-sectional data and there's longitudinal data. With cross-sectional data, the outcome variables and covariates are measured at a single time point. And with longitudinal data, each subject gives rise to a vector of measurements where these represent the same response measured at a sequence of different observation times. And so some characteristics of longitudinal data, which, by the way, is extremely prevalent in biomedical research, are that individuals are measured repeatedly over time. So that's again, the same outcome is measured over time for the same subject. The time measurements are taken, the time when the measurements are taken is not of primary interest and is often considered fixed by design, but still needs to be considered in the analysis. And you generally have a small number of observations per subject, but a relatively large number of subjects. That's an assumption that a lot of the longitudinal data methods make. And there are methods that exist for large numbers of observations per subject, but these tend to fall more under time series analysis or functional data analysis, and we're not going to cover that in this course. And finally, the variability of observed data can be divided into three components. And I have a separate slide for that because this is a really important feature of longitudinal data, and we really conceptualize longitudinal data as how do we talk about the correlation, the different pieces of the variance in the data, where the variance in the data can be explained by heterogeneity between individuals or heterogeneity within individuals, and then also by measurement error. And we'll talk more about these pieces in the next couple of lectures. And because longitudinal data analysis focuses on changes over time within individuals and differences among people in their baseline values of the outcome, it requires special methods that haven't been seen so far in this course. And in particular, this is because methods that assume independence of observations tend to be biased for longitudinal data. For example, consider a cross-sectional study that found that older people smoke more. There are a couple possible explanations for this finding. One is that people tend to smoke more when they get older, but this seems rather unlikely. Another possibility is older people grew up in an environment where the harm of smoking was less widely accepted. And if you just have a cross-sectional study, you can't distinguish between these two different explanations. But LDA can distinguish the effect due to aging, that is, changes over time within a subject in things like smoking status, from cohort effects, which are just the differences between subjects at different points in time or at baseline. And that's one advantage of longitudinal studies from that previous example. In general, other advantages are that each subject can serve as his or her own control. You can distinguish the degree of variation in Y across time within a subject from the variation in Y between subjects, Y being the outcome. And this is because with repeated values, you can borrow strength across time for the person of interest as well as across people. And so what this basically means is you can draw information both from repeated measurements within that individual and information from other individuals in the study to learn about your outcome of interest, Y. And then finally, because of the repeated measurements, you have increased power. If the measurements from the same subject were perfectly correlated, then you wouldn't, but this is rarely the case. So longitudinal studies tend to be more powerful than cross-sectional studies with the same number of subjects. So let's look at another example. In this plot, reading ability appears to decrease as children age. If you were going to fit a linear regression line through this data, it would look something like this, and you would say that reading ability is decreasing with age, which is a fairly not the finding that we might expect. However, if that had been longitudinal data, let's assume that instead of cross-sectional data, that was longitudinal data, and each child had been measured twice. And these lines now, each of these lines represent the data for one child. This is the same data that was plotted in the previous slide, but now that longitudinal structure is being taken into account in how it's plotted. And you can see actually for each child, reading ability increases with age, rather than the other way around. And without taking that longitudinal data structure into account, we would have never seen that, we would have missed this, the accurate direction of this relationship. So why do we need special methods for LDA? Well, repeated measurements from the same person over time tend to be correlated with each other. So that means that the assumption of independence that we've seen in all of the GLM models that we've considered so far tend to be violated. You no longer have independence of each of the different outcome measurements. However, what if we ignore that extra correlation, that violation of the independence assumption, and use standard regression methods anyway? Well, there are a couple issues with that potentially. First of all, correlation may be part of what we're interested in studying, for example, trends within a subject over time. This can also lead to incorrect inference. And you saw in the sort of extreme example with the child reading in the previous slide, this actually led to the opposite direction of the relationship than we would see if we hadn't considered the longitudinal structure of the data. But in less extreme examples, you can still get wrong standard errors, incorrect significance tests, and bad confidence intervals. And on top of that, you can get inefficient estimates of beta. You just don't. So there are several different types of features that longitudinal data can have. One is the outcome. So in longitudinal studies, the outcome variable can be continuous. For example, blood lead levels. And we're going to talk about mostly continuous data and longitudinal data analysis analogs to linear regression for most of the time. But it can also be binary, such as the presence or absence of lung cancer, or count, like we saw with Poisson regression, for example, the number of epileptic seizures. And the data can also be incomplete, meaning there's missing data or dropout during the course of the study, or it can be balanced or unbalanced, meaning the same or different numbers of observations and time points across subjects. And we'll talk about more about balanced or unbalanced data in the next lecture. Luckily, there are longitudinal models developed to handle all of these different features of the data, and we're going to talk about each of them. The models that we're going to consider that handle these different features of the data include linear mixed effects models, which are also called random effects models or sometimes multi-level models, generalized estimating equations, which are also sometimes called marginal models, and generalized linear mixed effects models, which is sort of the generalized linear model version of linear mixed models. So allowing you to have binary and count data outcomes. So finally, the things that I want you to take away from this lecture are, first of all, that longitudinal data structure arises from repeated observations on each experimental unit. And for this reason, longitudinal data sometimes more generally is called repeated measures data. The subjects, at the subject level, the units can be assumed independent of one another, but observations within subjects are not independent. And this has to be accounted for in analysis. So when I talk about correlation in longitudinal data, I'm talking about correlation within measurements made on the same subject. And then that comes up in the third point, where I say multiple responses within each unit or subject are likely to be correlated.